the universe continues its endless expansion, unveiling more of its mysterious and awe-inspiring nature. Since 1929, when scientists first discovered that the cosmos was stretching outward, our understanding of the universe has evolved dramatically. That discovery fundamentally altered how we perceive the universe's origin and future. But as our insights deepened, we came to realize something even more profound. Our own bodies are composed of elements forged in the fiery hearts of long-dead stars. By 1957, it became widely accepted that the night sky, far from being just a beautiful visual display, is in fact a window into the extraordinary physical forces that shape the cosmos. The universe is not static. It is in constant motion, teeming with unseen activity, mystery, and transformative power. Yet much of it remains beyond human comprehension, and we are left to ponder our place within this vast interconnected system. We question why we exist, how stars and planets formed, and whether other forms of life might inhabit distant corners of the galaxy. Still, it is often human nature to overlook such grand cosmic events until they become urgent or potentially threatening. One such case lies in the curious and increasingly unstable behavior of Betelgeuse, a massive red supergiant star located in the Orion constellation. Betelgeuse is no ordinary point of light in the night sky. It is an enormous star whose radius is over 1,000 times greater than that of our Sun, making it one of the largest visible stars. Though it lies more than 640 light-years from Earth, it appears unusually bright in our sky due to its sheer scale. In cosmic terms, however, this distance is immense. Even traveling at the speed of light, it would take more than 6 centuries to reach Betelgeuse, and with current propulsion technology, such a journey would take millions of years. This scale puts into perspective the enormous power contained within this distant giant, a power now drawing the attention of scientists due to its visible instability. Betelgeuse is classified as a red supergiant variable star, meaning its brightness changes over time. These pulsations are not random but follow specific cycles. A shorter one of around 185 days and a longer one that spans roughly 2,300 days. These fluctuations are the result of complex internal processes, mainly the expansion and contraction of its outer layers. When the star expands, it cools and dims. When it contracts, it heats up and brightens. These pulsations, like a cosmic heartbeat, reveal the turbulent and dynamic nature of the star's interior. What has become particularly intriguing and somewhat alarming is the increasing irregularity of these changes. In February 2021, Betelgeuse's V-band brightness dropped to 1.1614, one of the lowest levels recorded in years. This sudden dimming diverged sharply from its known patterns and led scientists to suspect deeper changes were occurring within. The reddish hue of Betelgeuse further adds to its uniqueness. This coloration results from a relatively low surface temperature of about 3,500 Kelvin, much cooler than the Sun's 5,500 Kelvin. Despite its immense size, the lower surface temperature causes Betelgeuse to emit less energy per unit area than our Sun. Recently, however, Betelgeuse has entered a more volatile phase, believed to be tied to fundamental changes in its core. Like all stars, Betelgeuse is powered by nuclear fusion, beginning with a fusion of hydrogen into helium. But in red supergiants nearing the end of their life, hydrogen becomes depleted and fusion shifts to the helium layer. This initiates a new process known as helium shell burning, during which helium atoms fuse into heavier elements like carbon and oxygen. Unlike hydrogen fusion, which occurs relatively steadily, helium fusion is highly erratic and turbulent, releasing intense fluctuating bursts of energy. These energy surges disturb the star's structure and drive powerful stellar winds that expel material from the outer layers. As this mass is lost, the star's internal balance shifts further, adding to its instability. The consequences of these processes are visible from Earth. Betelgeuse's light fluctuates due to the changing size and energy output of its outer layers. Scientists monitor this behavior using two primary methods: photometry and spectroscopy. Photometry involves tracking the light output of the star over time, creating light curves that help identify patterns and anomalies in its pulsations. Spectroscopy, by contrast, analyzes the light across different wavelengths, revealing information about the star's temperature, composition, and motion. These tools provide critical data that, when combined with advanced computer modeling, allow astrophysicists to simulate the inner dynamics of stars like Betelgeuse. These simulations use fluid dynamics, thermodynamics, and nuclear fusion physics to build predictive models about the star's future. A particularly fascinating mechanism at work inside Betelgeuse is convection. In red supergiants, energy produced in the core moves toward the surface through massive convective currents. Hot plasma rises, cools, and then sinks again in a continuous loop, creating a turbulent interior. These currents can produce massive upwellings of material that distort the star's surface and affect its brightness. When more energy reaches the surface, the star brightens. When less energy rises, it dims. The pulsing light we observe is a direct consequence of this dynamic internal structure. All these changes point toward Betelgeuse nearing the end of its life. Eventually, the star will no longer be able to maintain balance against gravity, and it will collapse in on itself. The resulting supernova will be one of the most dramatic events in the sky, briefly outshining an entire galaxy and dispersing the elements forged in its core across the cosmos. This fate, while likely still thousands or tens of thousands of years away, is foreshadowed by the behaviors astronomers are documenting now. Every fluctuation in light and spectral anomaly adds to our knowledge of how massive stars evolve and die. In this way, Betelgeuse serves as a powerful natural laboratory, helping scientists understand not just its own destiny, but the life cycles of massive stars in general. A stunning example of Betelgeuse's instability occurred during the Great Dimming of late 2019 and early 2020, when its brightness dropped to an unprecedented low. Initially, speculation swirled that this might herald an imminent supernova, but further investigation revealed a more nuanced cause. Observations from space telescopes like Hubble indicated that the dimming resulted from a large dust cloud. This cloud formed when a massive convective cell from the star's interior rose to the surface, cooled, and ejected plasma into space. As this material cooled further, it condensed into dust, partially blocking the star's light from our view. Although Betelgeuse eventually returned to its normal brightness, the event highlighted the unpredictable forces at play within red supergiants and emphasized the importance of continued monitoring. The study of Betelgeuse also helps scientists forecast the eventual fate of stars like our Sun. Though our Sun is not massive enough to become a supernova, it will one day expand into a red giant, shed its outer layers, and leave behind a white dwarf. The physical processes observed in Betelgeuse, fusion transitions, convection, mass loss, mirror those that will shape our own star's final chapters, albeit on a smaller scale. One of the most revolutionary frontiers in Betelgeuse's research is astroseismology, the study of oscillations within stars. Just as seismologists use earthquakes to understand Earth's interior, astrophysicists use stellar oscillations to infer the internal structure of stars. These tiny vibrations reveal differences in density and composition across the star's layers, offering an even more refined picture of what's happening deep within. For a pulsating star like Betelgeuse, this method is particularly powerful as it complements data from light curves and spectral shifts to give a fuller account of the star's behavior. In Betelgeuse, we see not just a cosmic spectacle, but a chapter in the grand narrative of stellar evolution. Every pulse, dimming episode, and convective surge is a signpost on a journey that ends in cosmic rebirth. When Betelgeuse finally explodes, it will seed the galaxy with the elements that may one day form planets, life, and even new stars. In a very real sense, we are made of star stuff born from the ashes of supernovae long past. And Betelgeuse offers us a glimpse of that beautiful, violent, and creative process in action. Through the lens of our most advanced telescopes and the minds of scientists who interpret their findings, we continue to uncover the workings of the universe, one dying star at a time. As we deepen our observation of Betelgeuse, it becomes clear that the study of a single star can yield profound revelations about the entire cosmos. This red supergiant serves as a microcosm of stellar evolution, a theater where the final acts of a star's life are played out on a scale almost beyond human imagination. Every burst of plasma, every pulse in brightness, and every layer of expelled gas is not only an indicator of the internal dynamics of Betelgeuse, but also a window into how stars shape the galaxy. Stars are not merely isolated balls of gas. They are engines of creation, playing essential roles in galactic chemistry and evolution. When Betelgeuse eventually meets its end in a supernova explosion, it will do more than mark the death of a celestial object. It will spark the beginning of new cosmic cycles. The heavy elements formed in its core, iron, oxygen, silicon, and more, will be hurled into the interstellar medium where they may become part of new stars, new planets, or even eventually new life. This recycling process is central to the evolution of galaxies, and Betelgeuse is a perfect case study for understanding this mechanism in real time. Supernovae are among the most violent and transformative events in the universe. They occur in a fraction of a second but leave long-lasting imprints that shape cosmic history. In the case of Betelgeuse, when that moment comes, the explosion will be visible even during the day for weeks or months. It will outshine the moon, casting shadows at night and altering how we experience the sky. Such an event hasn't been seen with the naked eye in centuries. The last supernova observable from Earth without telescopic aid was SN 1987A, located in the Large Magellanic Cloud 170,000 light-years away. Betelgeuse, by contrast, is within our stellar neighborhood, making its explosion a once-in-a-civilization spectacle. The scientific community is preparing for this eventuality with a mix of excitement and patience. Monitoring Betelgeuse involves a global collaboration among observatories, satellites, and space-based instruments. New techniques are being developed to study not only the surface of Betelgeuse but also the complex interactions taking place inside its core. Interferometry, for instance, allows astronomers to combine data from multiple telescopes to form a clearer image, revealing details about the star's surface and allowing scientists to watch its oscillations and convective cells unfold in real time. Moreover, space-based observatories like the James Webb Space Telescope, JWST, and Hubble play crucial roles in capturing wavelengths that ground-based telescopes cannot. JWST, in particular, with its advanced infrared sensors, can peer through the dust clouds that sometimes obscure Betelgeuse from Earth, giving scientists uninterrupted views of the star's activities. This continuous observation helps build more precise models of its internal processes and allows predictions to be refined with each passing year. The hope is that by combining photometry, spectroscopy, interferometry, and astroseismology, we can anticipate the final transformation of Betelgeuse with greater clarity than ever before. But Betelgeuse is not just a scientific curiosity. It is also a cultural and emotional icon. Since ancient times, humans have looked up at the night sky and found meaning in the constellations. Betelgeuse, as the bright red shoulder of Orion the Hunter, has featured in mythologies across cultures. Its fiery glow has symbolized strength, danger, and transformation. Today, as we understand more about its physical properties, it still holds symbolic power, now representing the incredible journey from creation to destruction that governs the universe. The knowledge that Betelgeuse could explode within our lifetime adds a profound immediacy to this celestial body. It reminds us that we live in an active, dynamic universe where even the stars are not eternal. At the same time, the study of Betelgeuse challenges our perception of time and permanence. The processes unfolding within it are slow on human timescales but rapid on cosmic ones. Its life has spanned only about 10 million years, yet in that short time, it has lived a life more intense than our sun ever will. When it dies, it will do so in a blaze of energy unimaginable in our everyday experience. Observing this unfolding story helps humans reconcile our own short lifespans with the massive timescales of cosmic events. It underscores the fragility and the wonder of existence, both our own and the universe's. Furthermore, the phenomena observed in Betelgeuse offer practical benefits for science and technology. The data gathered in studying its structure, oscillations, and atmospheric behavior feed directly into our broader understanding of stellar mechanics. These insights have applications far beyond astronomy. The principles governing fluid motion, radiation transport, and fusion reactions in Betelgeuse can inform nuclear research, energy development, and even climate modeling on Earth. The tools and software developed to simulate the physics of Betelgeuse are often repurposed for use in other complex systems where behavior must be modeled across vast ranges of pressure, temperature, and time. The lessons learned from Betelgeuse also influence our search for exoplanets and habitable systems. By understanding how massive stars evolve and die, astronomers can better evaluate the environments around other stars. For example, the explosive deaths of red supergiants often lead to the formation of neutron stars or black holes, both of which can have extreme gravitational effects on surrounding planets. Knowing how and when such events might occur helps scientists rule out or validate the stability of certain planetary systems in the search for life elsewhere. Ultimately, Betelgeuse is not an isolated subject of interest. It is part of a grand network of stellar processes that drive the universe's growth, change, and renewal. As its final act approaches, it becomes a beacon, both literally and figuratively, of what it means to live in a universe defined by cycles of birth and destruction. The awe it inspires is not limited to those with telescopes or degrees in astrophysics.